In chapter 8, we will be looking at addition reactions. This is one of the specific reactions of organic chemistry that we will be studying. First, we'll look at a general mechanism for the addition reaction. We'll define what is a mechanism, and then we will look at a specific type mechanism for these reactions. And then we'll apply that concept of the mechanism to the addition of HCl to alkenes, next HBr to alkenes, and the addition of Br2 to alkenes, and Br2 and water to alkenes. So these are the specific reactions that will be covered in this lecture. So these are some of the general reactions that we looked at in a previous chapter. The addition of bromine to the alkene to give here the bromine adding across the double bond. Note again, here is your functional group, so that is where the reaction will take place. By definition, the functional group is a region of the molecule where reactions occur. Here's the functional group again, the alkene, and here is the addition of HBr across the double bond. Same here. And this is the addition of water, H2O, across the double bond here to produce that as your product. Okay, let us look at the mechanism. The mechanism, by definition, is a step-by-step description of a reaction. So once again, it is a step-by-step description of a reaction. Of course, as you know from general chemistry, a reaction just does not occur all in one step, or most reactions don't. Some reactions occur by different steps. And the addition reaction is one example that is a stepwise reaction. So let us look at the mechanism. First, here is our alkene right here, the double bond. And as we have described before, it is really a Lewis base because it has here a pair of electrons, of pi electrons, that are available for reaction. A reaction with a Lewis base will occur with a Lewis acid. So here is a Lewis acid E+. We'll define it as E+. Why E+? Because we'll have another name for this. It's called an electrophile, or an electron-loving species. So that's another name synonymous with a Lewis acid. So these electrons here can bond to the E+. As you can see, if they swing out like this, here is a new bond, but it leaves a positive charge on the adjacent carbon. Notice it's on the adjacent carbon. These electrons can swing out the other way to react with E+ to form this bond here, and it leaves here a positive charge, which is also known as a carbocation, because it's a positive charge on a carbon, so it's called a carbocation. So once again, notice that this alkene here is not symmetrical. We have three groups bonded to the alkene that are the same, but then we have a hydrogen, so it's non-symmetrical. So that's why we have two possible carbocations here. So that is the first step of the mechanism. It's the addition of the electrons to the electrophile to create carbocations. In the next step, as you can imagine, if there is a nucleophile present, Nu, which we'll define as a nucleophile, which is also a Lewis base because it has an unshared pair of electrons. So these are synonyms that we'll use from here on: nucleophile, Lewis base, electrophile, Lewis acid. the carbocation here is in fact a Lewis acid and also an electrophile. So these electrons here from the nucleophile will react with the electrophile or the carbocation to form a bond right here. And as you can see here, this is a neutral molecule, so that is your product. There's another product though, because there is another carbocation that was generated from the initial reaction. So this nucleophile will react with the electrophile to form a new bond right here, and that's a neutral molecule, so that is another product. So the summary here of the mechanism, this two-step mechanism, is if you have a symmetrical alkene, such as this one, notice it's symmetrical because here's your line of symmetry right here. This half is the same as that half. So these electrons here, which are nucleophilic, will react with the electrophilic portion of a molecule to generate the E plus, the carbocation, and then the nucleophilic portion will react to form the neutral molecule. So this is your predicted product. Let's see if we can apply this. This again is a symmetrical alkene. So here is our reactant HCl. H is partial positive and the Cl is negative. So this H plus is our electrophile or E plus. This Cl will become Cl minus. It will be our nucleophile or Cl minus. So the H plus will add to this first to form the carbocation, and then the Cl will add to give our neutral product. So you should be able to predict the product of an addition reaction to an alkene once you have identified the electrophilic portion of the reagent and the nucleophilic portion of the reagent. Let's see another example here. Here is an example which is now not symmetrical, unsymmetrical. So it's possible to form two carbocations because these electrons can react with the electrophile to produce two carbocations, two different carbocations, and the nucleophile here will react to give two different products as we have shown before. Let us see if we can apply that to this reaction here. This alkene is non-symmetrical because this half here is different from the bottom half. In other words, the groups that are bonded to this carbon are different from the groups bonded to that carbon. So this is our HCl. Here is our electrophilic portion, H plus. Here is our nucleophilic portion, Cl minus. So the H plus can add here to give the carbocation, and the Cl will add to the other carbon. It's also possible for the H to add to this carbon, as we have seen here, and the Cl to add to this carbon to give this product. So you can see there are two possible products if the alkene is not symmetrical. Again, by symmetrical we mean that the groups that are bonded to the carbons of the double bond are not the same, which means they're non-symmetrical. Okay, let us see why we have two different products, and most important, let us see how we can determine which is the major product. So of course in organic chemistry, when you go in the lab, part of the job is to get a large percentage of a organic product, the major product. So if we have in two products as possible products, how can we determine which is the major organic product? Let us look at the mechanism to determine which is the major organic product. So let's look at the first step again. The first step is that these electrons here, the pi electrons, will bond to our electrophilic portion of the HCl, or the molecule, to produce carbocations. There are two possibilities, because the H can add to this carbon and the H can add to this carbon. So if it adds to this carbon, we have this carbocation. If it adds to this carbon here, we have this carbocation. As you will see, these two carbocations are different. This carbocation here has a positive charge on this carbon, which is bonded to 1, 2, and 3 other carbons, so therefore it is a tertiary carbocation. This carbocation here has a carbon, or it is on a carbon that's bonded to 1 and 2 other carbons. Of course, the other bond is to hydrogen, and this is described as a secondary carbocation. Now, let's see the difference between secondary and tertiary carbocation. One is more stable than the other. As you can imagine, a positive charge needs electrons. So the more alkyl groups that are surrounding a positive charge, which has bonding electrons, that would be more stable. So the tertiary carbocation is more stable than the secondary. The trend is actually here. Tertiary is more stable than the secondary, which is more stable than the primary, and a lot more stable than the methyl. So the stability of carbocations, this is the trend. Tertiary, more stable than secondary, and secondary, more stable than primary, and a lot more stable than your methyl. Let's see what's the importance or the relevance of the stability here. The bottom line is that this Cl minus, or the nucleophile, will react with the tertiary carbocation to produce the product, which is the major product. Why? Because it is coming from the more stable, that's the key, the more stable intermediate. So once you have a more stable intermediate, it will produce the major, it will go on to form the major product. The Cl will also react with the secondary carbocation here, but that becomes the minor product. So now it is possible to predict the major product and the minor product based on an addition of an HCl, for example, to an alkene. Okay, let us see what's here. So this gives you a graphical description of these reactions. So if you have your alkene here reacting with HCl, for example, it goes on to form two carbocations, intermediate, the secondary and the tertiary. You may recall that anything that's lower is more stable, anything that's higher is less stable. So the reaction path will prefer to go through the more stable intermediate, which is the tertiary carbocation, to give you products. The secondary is less stable. The reaction path prefers not to go through that reaction path because it requires more energy. So therefore, the tertiary carbocation is the intermediate that's more stable and will give the major product. Okay, so let us look at this. So based on what's shown here, you should be able to predict the major product here. So propene reacting with HCl, two products, you should be able to predict this is the major product because the carbocation that's formed here is the secondary carbocation, and the carbocation that's formed here in the mechanism is the primary carbocation. Since the secondary carbocation is more stable than the primary, this is your major product. Here's another example. Methyl cyclohexene. This alkene will react with H plus to form two different carbocations, as we have seen before. The tertiary is more stable, and the Cl will react with the tertiary to give this as the major product. And of course, the minor product is formed from the Cl reacting with the less stable secondary carbocation. So you should be able to write a mechanism for these type reactions. Let us look here at Markovnikov's rule. So what this rule is basically stating, Markovnikov is a Russian chemist about quite a few years ago. What he did quite a few reactions, and he observed. Here is his observation. He observed that if we're adding HX, okay, here is HCl, for example, where Cl is the nucleophile, the hydrogen always adds to the carbon of the double bond that has the most hydrogens. So this carbon here has 2 hydrogens, and this carbon here has only 1 hydrogen. So what he predicted is that in the addition of HCl or HX, where X here would be the nucleophile, the H always adds to the carbon of the double bond that has the most hydrogen, and the nucleophile adds to the other carbon to give the major product. So oftentimes you'll see this as the Markovnikov product. It's the major product based on his prediction. This, of course, is the minor product because that's not what he predicted as the major product. So let's see if we can use Markovnikov's rule here to predict the major product for this reaction. So here's a carbon of the double bond, or here's 1. It has no hydrogens bonded to that carbon. Here's the other carbon of the double bond. It has 1 hydrogen bonded to it. So this hydrogen will add to this carbon, and this chlorine will add to that to give the major product, or the Markovnikov product. So you should be able to predict the major product of these reactions. What you will see on the quiz and on the exam from here on is the wording would be no longer predict the organic product, but it will be predict the major organic product for these reactions. So in other words, you would just give this as the major product for that reaction. Okay, let's see another observation that's made in the lab. So if you went in the lab and you carried out this reaction here, you'd expect HCl to add across the double bond here to form 2 products. Notice these 2 products would be formed in equal amount, or predicted to be formed in equal amount, because what's formed here is a secondary carbocation after the addition of H plus, and a secondary carbocation after the addition of H plus. And then of course Cl would add to give this as 1 product, and here as the other product. But if you went in the lab and did this experiment, you would observe this as an unexpected product. So after you finished your reaction and you did your isolation, you would see that this is a product that's probably the major product, and it's one that's unexpected. As chemists and as scientists, we're curious. So we're curious to find out, where did this product come from? How was it formed? So our question is, how was this product formed? So to determine that, we'll have to look at the mechanism. So let's look at the mechanism for the reaction to form this product here. So the first step, as you can imagine, is the addition of these electrons to the electrophile. Remember, this is the electrophilic portion of HCl to form here our carbocation, and that's a secondary carbocation. A secondary carbocation can become more stable as a tertiary carbocation if, look at this carefully, if this H with its electrons here migrated to this carbon. So if we take this H with its electrons, it's called a hydride, and move it from carbon 1 to carbon 2, so we call it a 1,2 hydride migration or shift. Here it is. And now you can see that this carbocation is a tertiary carbocation. So it's more stable than your secondary carbocation. So the driving force for the intermediate to go from a secondary to a tertiary is because the tertiary is more stable than the secondary. Once you have the tertiary carbocation, you know what should happen next is the Cl minus will react here to give your unexpected product. So that would be the mechanism. It would be a three-step mechanism where, of course, let's go back here for a second. This would be the first step of the mechanism. Step number 1. Step number 2 would be the hydride migration. Step number 2. And of course, step number 3 would be the addition of the Cl minus to the carbocation to form the unexpected product. So there are 3 steps for this mechanism, and as we have defined earlier, a mechanism is a step-by-step description of a reaction. So here's a classic question that we typically ask students is, if you have this as your starting material, here is an unexpected product. How is that formed? What is the mechanism for that? So let us quickly see if we can figure it out. So notice there are 2 methyl groups on this carbon. On the unexpected product, it's only 1, and it looks as if the methyl group has shifted, or one of these methyl groups has shifted to this carbon over here. So once you have done that analysis, you know what should happen. So when you're asked to write a mechanism for a reaction, please carry out the analysis first. As scientists, our job is to carefully observe, make observation. Here's the observation. 2 methyl groups on this carbon. 1 has migrated over to this carbon, and it's shown here. So in your mechanism, you'd have to carry out a methide migration. So in this case, it will be a methyl group with its pair of electrons, and that's called a methide anion or methide ion. So it's called a methide migration, since it's moving from carbon 1 to carbon 2. So therefore it's a 1,2 methide migration. So the same 1, 2, 3 steps, same 3 steps can be used to explain the formation of this unexpected product by writing a 3-step mechanism. Okay, let's look at this reaction here. So if you went in the lab and your job is to get the product that we have called the minor product before, let's say you wanted that to be the major product. How do you do that? As you can imagine, you would have to use different reagents, and the mechanism would have to be different. So if you added HBr to this double bond right here, to this alkene, you'd expect this to be the major product based on Markovnikov addition. Here is the H. Here is the carbon that has an H right here. So we'd expect this H to add to that carbon, and this bromine to add to this carbon, and that is the Markovnikov addition to give the major product. But let us say you wanted this as the major product. So this is now your anti-Markovnikov product, or your anti-Markovnikov product. where the bromine adds to this carbon and not to the other carbon. The question is, how do we do that? As I mentioned earlier, the reaction conditions and reaction mechanism has to be different. So here are the reagents. HBr, key in the presence of a peroxide and heat, you will get the Anti-Markovnikov product. So you use the same HBr, but in the presence of peroxide and heat, you will get the Anti-Markovnikov product as the major product. Since we're chemists and scientists, we will have to understand why that is formed or how that is formed. So we'll have to look at the mechanism. So let us look at the mechanism. The first step of the mechanism is the breaking of a peroxide. Here's a peroxide, two oxygens that are bonded to each other by a single bond, and of course we have R groups bonded to it. In the presence of heat, energy, you can imagine this bond breaking right here to produce radicals. Notice these are radicals. They are not cations anymore. These are radicals. One electron on each of the species here. So that's a dot. So whenever you write these mechanisms, make sure you put a dot. A dot here means one electron, an odd electron. So the first step is to create the radicals. The next step is the radicals will react with HBr to form the stable alcohol here and Br dot. You may recall that Br dot is pretty stable, so but it's an intermediate, so it's reactive, but it's fairly stable because of its size. So here's an intermediate. So the next step of the mechanism is the Br dot will now react with one electron of those two electrons. One electron. So what happens is that Br, here two electrons here, one from the Br dot and the other one from the pi electron. So what's left behind is a radical. Notice it's not a carbocation, it's a radical. So this is a tertiary radical if it bonds here. If it bonds here, as shown here, it forms a secondary radical. So you know where this is going. So we have two possibilities here of the radical, a bromine radical, reacting with an alkene. Two possible radicals. One is a tertiary in this case, and one is a secondary in this case. The stability of radicals is that tertiary are now more stable than a secondary, and more stable than a primary, and more stable than a methyl. So the stability is a tertiary is more stable than a secondary and more stable than a primary, as shown here. So the trend is the same as for the carbocations. In this case, it's a radical, however. Tertiary, more stable. So you know what's going to happen next is that we can form two products where we have the bromine radical reacting with the HBr to form this product here, and of course another radical because it takes two electrons to form a bond, and one is here already, so it takes one from this bond, leaving a third here. So this becomes the major product because this is the tertiary radical. And of course this is called the Anti-Markovnikov product, or the Anti-Markovnikov product as the major product. The secondary radical, which is less stable, takes one electron from here and bonds here, and of course the other electron forms the Br dot. And of course this is the minor product. As you can imagine, these are radicals, so they will react with something else to form a neutral molecule, and that's shown here where these bromine radicals couple to form bromine gas, bromine product, and it can couple with the RO dot to form ROBr. So we have here neutral products. So, as a summary, if you have this alkene here, notice this is an alkene reacting with HBr, in this case in the presence of a peroxide and heat. That's what makes the difference between what we've seen before. The Anti-Markovnikov product is the major product where the bromine adds to that carbon to give this as a product, and this is now the minor product. Later on we'll start doing synthesis, where you will need to make these intermediates as you go along. So sometimes you need this as the major product to make another molecule, and sometimes you will need this as the major product to make another molecule. So be careful with your reagents. If you just use HBr by itself, you get this as the major product. If you use HBr in the presence of peroxide and heat, you get this as the major product, or your anti-Markovnikov product. So again, we will take off points if you do not include the reaction conditions, complete reaction conditions that's needed to make the desired product. Okay, let's look at the addition of bromine. Here is bromine, or Br2, to an alkene. So as you can imagine, bromine, look at the periodic table, you can see that bromine is in the middle of the right, so it's fairly large. So these electrons, and polarizable, should I say, they're very large and polarizable. So at some instant, this bromine here can be partially positive, and this bromine here can be partially negative because it's large and polarizable. So these electrons can react with this positive end of the bromine. But the trick is that it does not form an open carbocation because the bromine is so large. It basically sits between these two carbon atoms. So it sits on top of these two carbon atoms here. We call that a bromonium ion. Okay, but it's an intermediate. It's a charged intermediate. Then we have this bromine here that's floating around. It comes in from the opposite side. Keyword here is opposite side. So just imagine that this bromine is sitting like on top of a table, which would be these two carbons. And then this bromine is coming from below the table to form here the product. That's why it's called a transaddition, because this goes on top and this goes on the bottom, or opposite sides. So they go on opposite sides. So we say that this addition is stereospecific because it gives a specific stereochemistry. So what you'll see from here on is predict the major organic product, include stereochemistry where appropriate. So if you gave me, or gave the grader just straight lines here, it would not be totally correct because the stereochemistry must be pointed out. Here's an example. So here is the alkene functionality. Here's bromine. The solvent is typically carbon tetrachloride. It's an addition reaction. But notice the stereochemistry here is trans. Make sure you put trans, a dash and a wedge. Here's another addition. Reaction to the alkene, bromine, trans addition, dash and wedge. So here's a dash and here's the wedge. So do not put straight lines because straight lines do not indicate stereochemistry. They just indicate bonding, but nothing about stereochemistry. Okay, let's look at a reaction here, and this is in the presence of water. So we're adding bromine in the presence of water. So as you can imagine, bromine is very reactive, polarizable. So this end here, it's possible for one end to be partially positive. So these electrons here, which are nucleophilic, will react with the electrophilic end of bromine to create again the bromonium ion. Here we have a competition because we have the nucleophile bromonium anion, bromine anion, and if you introduce water, notice we have here an unshared pair of electrons. In fact, we have two on water. So that's nucleophilic, Lewis base. So this Lewis base can react at this carbon or at this carbon. Here's the trick. It will attack the carbon that's most crowded. So in other words, here is a hydrogen, which is not written in. And here is an alkyl group, and a carbon. So it attacks this carbon here because it is most crowded and not this carbon. So it does not attack that carbon, and this is the intermediate. And of course, bromine can pull off this hydrogen here as HBr, so this is your product. Notice, key here is stereochemistry. Trans. This OH and this Br are trans to each other because this bromine is sitting on top of these two carbons here, and the water is coming from below to attack that carbon. So that's why the product is trans. So again, make sure the question will read, predict the major organic product for the following reactions and indicate stereochemistry where appropriate, and you'd have to use dash and wedge to indicate stereochemistry. So here is an example of what we just did. If you're asked to predict the major product, so this would be a question mark right here, and you're asked to predict the major product here. You can see here this is bromine in the presence of water. This is a nucleophile. As we have seen, the bromine will form the bromonium ion, and the nucleophile will attack that bromonium ion to give trans stereochemistry here, called a bromohydrin. Here's one that's not symmetrical because this carbon here is different from this carbon here. So the bromonium ion would form right here, and then the water would attack this carbon because it is more crowded than this carbon right here. So this is your major product, and here is your stereochemistry trans. Okay, I think this is the last slide. Yes, it is. So, so this is the last slide. This covers only a portion of this chapter. So your quiz on Thursday will cover through this portion, sections of the chapter. I will post the rest of the video for the rest of the chapter later on in the week. So what I'll do is I'll post this video along with the PowerPoints. So if you want, you can go along with the PowerPoints depending on which one you find most helpful. So continue to study hard, read your textbook, and work the problems. The tutorial problems that you got are very helpful in applying this information. So continue to work hard and get ready for your quiz on Thursday. Okay? Bye.